Hello everyone, so in the last few tutorials we have been trying to simulate an industrial robotic arm called GP7. So in this video what we'll do is we configured the ROS package, MoveIt package last time, MoveIt config package, and now we'll add the controllers in it. So as you can see, I think the kit started again, so I think so let's see. We had this visualization package. Within this we had this control gazebo launch file, and if we launch this file from ROS, so we'll have to make this package from the cat Namespace, and then I'll have to source it, and then I will do GP7 visualization, and there is control gazebo package. So if we run this package, we'll see that we have this arm, and it has a controller which we can, if we run ROS joint trajectory controllers plugin, we can see here under controller manager. So it's a little, like, you cannot see it because of the resolution of the computer, but like these are the joints that we can control. So if I'm changing the base joints, it's moving. Yep. So I'll make all the joints come to 0. So there are a few things that you should know. So how is that working is, so if we examine our launch file, we'll know that we started the gazebo as an empty world. Then we uploaded the robot URDF file in the parameter server as robot description, with the name of robot description, actually robot underscore description. And then we use a node called URDF spawner to spawn the robot, but using the parameter. That's why there is this param switch, and these XYZ, and then you can also, like, where should the robot spawn, where should it be spawned. So you can spawn it in any XYZ location, or in any rotation also, and what should be the joint values you can pass in here, but I'm not going to do that. Then you load, similar to how you load the URDF into parameter server, you load these controller configurations into the parameter server. So as you can see, the controller configurations are in robot description config joint controllers.yaml file. So if I go here, you'll see that we have this joint state controller first, and then we have single joint controllers as position controllers under the namespace of GP7 robot, and then we have this arm controller, which is basically a trajectory controller. So you can think of these joint position controllers as the single PID controllers, which is controlling each joint, but the problem is that you basically want trajectory controllers where like each like if you give a point, if you give like a desired positions in joint space, then it basically cuts these from the start position to the desired position. It cuts these into trajectories, like small points, and it follows the trajectories instead of just a single set point position control. And we actually need joint trajectory controllers or group controllers for MoveIt configuration. And so we had we also did one more thing. So if we go under MoveIt config and launch file, MoveIt package and launch file, so we'll see that we have a demo launch file here. What it does is, I just close this one and I'll source the workspace again because I'm in a different terminal, and GP27 visualization demo launch. Yeah, so it will open ROS, and when we configure MoveIt, so what happens is that it auto generates some launch files, but it does not attach the controllers with the MoveIt. So it's basically called fake controllers, so you can basically move around, but they don't really work like in physical simulation. So you have to manually attach these controllers, and the way to do it is basically, it's actually quite simple. What you do is, normally if you look at ROS packages of other robotic arms, so let's say that this file basically comes in, and so what happens is, when you have this giant controller, trajectory controller, and you put these configuration in the ROS parameter server using this launch file, and then you spawn this using this controller spawner node, and then this controller gets attached to your robotic arm because you actually configured it in the URDF, and you start this robot state publisher, which we'll talk about I think in a minute. So now this joint trajectory controller, arm controller, basically arm controller is the joint trajectory controller. So this this starts certain nodes, this starts an action server and a topic of command. So if I start it, I can show you. So if I'll do ROS topic list, so basically action server comes in, are listed in ROS topics. So you will see that this is an action server, and this is basically a topic to control this if you want to do it directly from the ROS controller, from the ROS topic. But like, this is not a recommended way. You should always use action server because they can be interrupted and all that. So one more thing is, a minute ago I showed this plugin which you can use to like, it's a small GUI that you can use to check if your robot controllers are working. And what this plugin is doing is, basically it's publishing these joints directly to this topic, and like, there is a simple way to check it. Is if you echo, okay, 600 GP7 arm controller command, so you can see that the topic I'm subscribing to is this topic, and I'm echoing it in the terminal, and the first joint position is 0.8, which is here. It's also 0.8, but it's very small, so you cannot, like, it might be not visible, but if I change it, you'll see that it's changing. The first joint value is changing. So the controller, so like, how these are working is like, to put things in perspective. We have in the URDF, which one? This one. If we go down, and we had a gazebo tag here. Yeah. So we have this lib gazebo file, and it's basically a C++ compiled file. So it uses the gazebo DAF packages to what it does is that it looks at the parameter server, the URD, and looks at the parameter server, sees that there is a controller config file, and then it looks at these transmission tags, and it sees that these joints are the ones that are controllable, and and then it looks at the controller config file and sees that this joint has the limits of, like for example, -pi to +pi, and it should be position controlled. So in the gazebo it changes the position of that joint because it's a simulation, it's a physical simulation, so it can change that position. And while it changes that position, it also publishes the joint states, and the joint states are published only when we configure this joint state controller, which is basically like, see, you can say it's a controller, but it's only publishes. You are not actually controlling anything, so it serves as a feedback. So you can see that if you look at joint state topic, it must be under GP7 and GP27 joint states. So you can see that only those joints are being published for which we use the transmission tag, because transmission tags tells this libgazebo that these joints are controllable and you should publish only these joint states, not the others. You can have fixed joints, but it won't publish those joints states because they are fixed. So that's how this is working. So this joint states work as a feedback for the controllers, and it sees that where is the joint, and then it goes, and if the user defines if the user publishes or connects to this action server and sends a trajectory, so it follows the trajectory. Now how the MoveIt works with all of this is basically you have to connect the MoveIt to this action server, and to connect it is very simple. So okay, there is one more thing that I have to explain before moving on, and we have this thing called a robot state controller, robot state publisher. So robot state publisher is basically like it takes the joint state topic and then it finds the TF of like how the TF tree has changed accordingly. So there are two ways to visualize this. Basically, I'll close this and close this. So one way is if you run rqt, not rqt node, I forgot the name. It's how do you visualize node? Sorry, rqt graph. Yeah. So if you look at rqt graph now, and it's very small. Yeah. So you see this topic, joint state topic. So it's like a robot state publisher, which is basically I think a Python node, or I think it's written in Python if I'm not wrong. So this joint robot state publisher node subscribe to the joint state node, and it sees that okay, so we have a basic definition of robot frames like robot frames, which is the forward kinematics in the home position. And then if the joints changes, then accordingly how frame changes according to them. So the robot state publisher subscribe to this joint state publisher, and then it publishes a TF tree. And to visualize the TF tree, one easy way is that I'll first source this. So I'll run ROS, and because so I hope you know that ROS is a visualizing tool. And what you can do is first change this fixed frame to the world frame, or like the fixed frame in your URDF. In my URDF it's world. I know it's very small, but like I'm sure you can probably not see this, but let's continue. So I'll add a robot model. So if you go and click on add and then robot, you'll see a robot model here. And as soon as I add it, what this robot model does, it takes it searches the parameter server and sees that there is a robot description file, robot description parameter, and robot description parameter basically describes the whole robot, how it looks and what meshes it's using. So it subscribes to that, it basically takes in that package, and as you can see that robot description is under robot description parameter, and then it gives this whole like how these links are connected and everything, and that's why we can visualize this. It's not a physics engine, ROS is just a visualization tool. Okay, so if you want to visualize the TF tree, you can click on add again and then TF, I think TF is not, yeah, it's publishing right now. So you can see that this TF is being published here. And like to properly visualize it with the robot, what you can do is go under the robot model. There is this alpha value, which is basically the transparency value, and I'll change it to 0.2. And now you can see how the frames are connected. And I think it's pretty cool, because like, you know, the concepts of forward and inverse kinematics and how the frame, it's very difficult to visualize, and this TF gives a very nice representation of these like these frames, instead of solving them in your head. So now what this robot description is doing, if we start RQT joint trajectory controller now, like this is a plugin, so start now, we'll see what's happening. So I'll connect to this controller, and as you see, if I change the joint value, the robot moves, and with the robot, because I changed the base, because I changed the joint 1, so all the frames will move accordingly, because they are in reference to the base frame. Like the second link, first link frame is in the the second link frame is related to the first link frame, so that's why this frame will move also. So this TF update is done by the robot state publisher. So if I don't start this, if I don't launch this under my node here, so it will not update the TF tree, and it will be problematic later on. So this is how the TF and robot state publisher, joint state publishers are connected to each other. Joint states are connected to each other. Okay, so I hope this was helpful. There is also another thing called joint state publisher, and that's used for a completely different reason. It's used, for example, if you have, for example, a gripper, and if the gripper is under a different namespace. So if you can see that, like you had noticed that our controller was under GP7, right? And GP7 namespace, and like if our gripper was under another namespace, then we'd have two different controllers under two different namespaces, and then like we'd have to bring them into the same namespace so that robot state publisher can subscribe to them, right? So one easy way to do that is using this robot joint state publisher. What it does is basically you can source it so that different, like you can remap the topics to the same namespace. There are other reason to use this. One more thing is, for example, if you don't have a controller for something, let's say you have a gripper and you don't want to write the controller for it, you can use this joint state publisher, and what it will do, it will publish random joint states for that. Random by random, I mean like you won't have to give the desired value, that will just randomly publish the joint states in the joint state topic. So I hope that was that's clear. Now so we have our MoveIt configuration, we have our joint trajectory controller working. We saw that how TF is working and connected to robot state publisher. Now what we have to do is we have to connect this this action server to the MoveIt. So MoveIt action client, MoveIt controller client can connect to this, and when we change something using MoveIt, so it will publish it, like it will move the robot. I think I actually recorded a video before and I was making changes in it, and what happened is that like I couldn't properly record it, so I already wrote this file, so I thought that instead of rewriting it again, I'll show you here. So when you will install this, when you'll have this file, so there is this ROS controller file which is for the fake joint controllers. So you should not use this file. You'll have to create another YAML file under the config folder, or anywhere. You can make it anywhere, but it's easy to maintain it within the MoveIt config package. So it's a controller.yaml file. You can rename it to anything you like, just like it should be meaningful. Then you write all the controllers that you have should be under controller list namespace, and as you can see, I have the name of the robot as GP7 / arm controller. Action server namespace is basically joint trajectory controller. As you can see that if you follow this, so first is the name, so this is the name. Oh, sorry, starts from here. Yeah, ARM controller till here, and then the action server namespace is joint trajectory controller, so that's why I wrote follow joint trajectory. The type is follow joint trajectory controller. There can be other types like group controllers and joint group controllers, but I'm using follow joint trajectory controllers. It's the default controller for it. It's true because normally you can have multiple controllers for the robot. So for example, you can configure joint controller, joint position, trajectory position controller, trajectory speed controllers, and trajectory effort controllers. And then, like for example, if you want to switch from position to speed controller, you can do that, and it's for later videos. But yeah. And then what are the joints in it? So I have written the name of the joints here. So for example, if I had a gripper also here, so I would do something like this. Gripper, the name of the gripper would be something like let's say robotic gripper, so robotic 2F85. I would name it something like this, and gripper command controller, and then I would have like it's under this name. I have to write action namespace. It would probably be a follow joint trajectory. So, and then like I'll do everything like this. Okay. But currently I don't have any gripper connected to it, so this is only one controller. Now we have to do certain changes in the launch files, and to do that, what I have to do is basically I have to upload this controller file into the parameter server, and the way to do it is like this. So under the launch file, so we are doing everything, we are making every changes in GP7 MoveIt config folder. So there are two folders, one is config, one is launch. We created a file under ROS under config folder called controllers, and we wrote this, right? So then we go under demo. Like it's easier to back follow it from the launch file, so it's like it will be much easier this way. So if we go here, we'll see that like this is all MoveIt stuff, but joint state publisher is publishing the like fake joint state values. It then publishes robotic state publisher, and here is move group, MoveIt ROS. So we'll go under move group dot launch file. So if we go under move group dot launch file, move group, yeah, this file, so we'll see that it's starting the planning context, and then there are these params for move group, and allow trajectory execution dot launch file. So this seems like something which is related to controllers because it's a trajectory execution XML in this. So I'll go under this file, which is trajectory. Where is trajectory? Yeah, trajectory execution launch file. So if I follow this, it will take me to another controller manager. So MoveIt controller manager, it's under MoveIt controller manager, and it will be named as robot name underscore MoveIt controller manager, which is basically this file. So if I come to this MoveIt, so it's like I know that I'm changing files again and again, but I'm back following from the launch file. So as you can see here, so this was the load ROS controllers to the parameter server. So instead of doing this, I changed this ROS from ROS controller to controllers.yaml file. Now what's happening here is basically I'm using ROS, but I'm telling MoveIt by uploading this launch file, uploading this YAML file that connect to this, that my controller's action server is basically this, so connect to this server. Okay, before this file, which is ROS underscore controllers.yaml, it was telling it that use basically fake controllers, so we are not going to use that. Okay, so that's that. Now what we can do, there is actually one more thing. Instead of like running this file, what I'll do is I'll take this move group, and instead I'll take this move group, and so this is starting move group, and this is starting MoveIt ROS config, like MoveIt ROS file format. So I'll take this, I'll go and under my visualization, I'll instead I'll start it here. Okay, so after the robot state publisher, I'm starting the move group launch file, and it says that allow trajectory execution. It takes this argument which is true. Fake execution, I'll say false instead. What I'll do is, yeah, okay, false. And info, I don't think I need this, but I'll remove debug, or I'll just say it'll pass false to it. As for GP, MoveIt ROS config is true, debug is false. So just to summarize, this launch file basically starts the move group, which starts launch planning scene and everything. And this is basically starts ROS, and ROS with specific config file which is configured for MoveIt. Okay. So let's see what happens. So I'll run this control_gazebo launch file again. Okay, so first started the ROS, it started the gazebo, and it also started this MoveIt, right? As you can see. Yeah, so it's always good to have a look at, keep looking at the terminal and see if there is an error, or even if there isn't, it's very important. So it tells us a few things. So first it tells us that the kinematics plugin failed to load, so it's very important that you should install kinematics plugin. So I'll install it in a minute. And so if you go a little above this move group using, there is this thing which is very important, return one controllers in the list. So we had one controller, and it the move group controller client connects to this controller server. So I think we do not have the kinematics plugin installed, so I'll see. So under MoveIt config, if we go in the kinematics, it's using track IK, and it says that we don't have track IK installed. So I'll do this ROS update ROS sudo apt-get install ROS melodic track IK git track IK, and I should install track IK. I think that was the error here. The kinematics plugin ARM failed to load. So the ARM kinematics plugin is basically, there are different kinematics plugin, by the way, that you can use. I'm using track IK, which is better than fast IK and KDL, because KDL is sort of like a probabilistic, it uses a probabilistic method to, not a probabilistic method, sorry, it tries to optimize is the difference between the current joint values and the desired joint values, something like that. Whereas fast IK uses a deterministic method where it has already solved for the joint values and it's super fast. But the problem with the IK fast is that it's always either gripper up or gripper up or down. You have to do a lot of things to generate the fast IK for your robot. Track IK is somewhat in the middle of that, performance wise. And did it install? Okay, so it has installed, so I'll start again. So now we don't have that error. We also have returned one controller. Trajectory execution is managing controllers. Everything looks good, and we are ready to go. Not go, ready to test. If it's So as you see that last time we loaded this ROS, there was no this arrow, there was this like it's called marker, I think, simple marker. There was no this simple marker, but now we have this marker because there was no kinematics plugin, so it did not know how to place a marker. So now if we move this robot up and down, should we be able to move it? Let's try from goal state. Go to, I'll plan this and I'll execute it. So it keeps on executing this, and if we look in the gazebo, it did not work. Okay, so there is a problem here. As you can see, the problem, like I can tell you what's the problem is. The problem is that MoveIt is looking at / joint state topic, and our joint states are basically published in gp7_robot and joint states. So there are different ways to solve this. What I'll do is I'll remove namespace from everywhere, and then we'll be able to fix it. Another easy way is to remap our joint state topic to like / gp, like we should remove the namespace from our joint state topic. So I think because it will be problematic later on also, so what I'll do is I'll remove namespaces from everywhere. I don't know why I initially put them, but let's start from URDF, and I'm doing it there because like it's easier to just remap the topic, but I think it's better if we do it like this. So first in the URDF where we had this gazebo tag for this, I remove the robot namespace to only /, or in fact I'll not input / here. Then the second thing where we put namespace is in the controller config. So we have this robot GP robot, so I'll remove this, and then I'll have to, like, you can select control, and then in our like in Visual Code you can control, and there is this bracket, opening bracket, you can do that and it will indent like this. So you have to back indent, yeah. So we are only using this controller and this controller, by the way. Okay, then we loaded this joint controllers into our controller gazebo file, and here we loaded it, and here we told this controller spawner, and we said that the namespace is gp7, so I won't do this. So these are the 3 places that I have to change. There is one more place where I told the MoveIt config under controller that my controller namespace starts from this, so it starts from basically ARM controller. Okay, so when I start again, there is an error in the controller file. I think I don't have to use this. So a few things. Now if I see at ARM control, so you'll see that there is no namespace for GP27. If I look at for example, let's grab joint states, there is no namespace for that. In fact, I wrote joint. Yeah, there is no namespace. Why this is happening? I'll have to, I think in the robot controller, robot state publisher, I messed up something. Let's see. Yeah, so here I rename the robot state publisher, so I should not do this also in the launch file, because I changed the namespace. So now robot state publisher initially looks at joint state, and this argument was basically making it look at with this namespace. So because I removed namespaces, so I don't need this anymore. Okay, so I save this. So I should not have, now I just have joint states topic, in this command topic. Okay, so we have this robot. I'll move it here and move this robot here. Yeah, so everything seems to be working. If I move this robot now, God. Let's see what's wrong now. Oh, nothing. So it moved, and I actually don't like this when it keeps on rotating or like moving like this. So what you can do is you can go under MoveIt motion planning in ROS. Under plan path there is this option of loop animation. You can change it and then you can control S to save this configuration. Yeah, so now if I move this robot, why it's not? I'll use this goal state from here, and you can do random state. Oh, I think random valid is better, and we can plan it and execute it, because it's not a exactly physical robot simulation, so it's easy to like, because in real robot if you don't plan it and see how it will go, then can it anything. And believe me, these accidents have happened with me. So as you can see, so just to summarize what's happening, instead what we'll do is we'll run RQT graph. So RQT graph is basically just very nice. I'm running it here, it's out of screen. It's a very nice representation of how nodes are connected in ROS, and like, so here it is, and yeah. So this was controller spawners. Spawners are basically simply spawn something and then they finish, like they kill themselves, like the node kill themselves. It's like very bad terminology, I think killing, but yeah. Similarly, we have Gazebo GUI running here, and here is it. So robot state publisher publishes TF static, which takes in by move group, and before it was not working because move group like this was under different namespaces, and move group is connected to this. You see this controller, arm controller, follow joint trajectory controller, cancel, and then it sends this trajectory to Gazebo, and Gazebo sends feedback to move group. Gazebo also sends, because we have initialized a robot state publisher, state controller. So Gazebo also publishes a topic called joint states, which is subscribed by robot. So now what's move group is doing is basically why it's important to use MoveIt, and like why it's very like, I mean appeal to people is because there are different things that you can do with it. For example, up until now, if we had not configured move group, we were controlling the robot using its joint values. But now if you look at it, we are basically controlling it based on its like it's doing all the inverse kinematics and then finding the joint values for those desired joint poses, and then based on those joint poses it finds the inverse kinematic values, like the joint values in joint space, and then from the current joint space to the, it sends that joint desired joint poses inverse joint values to the trajectory controllers and keeps it like, then the robot follows that position and then comes back. Also one small thing, as you can see here, the goal state, we have this home and stand up poses here. So if you click on it, so it's a predefined pose that it goes to, the robot goes to, and I think one easy way is, like, I'll show you how to add more of these poses. You can do it programmatically also, but that works only for that node and for that session. and you can do it permanently also by just changing a few things in the srdf file. So if we go under the code, if we go here under, like here in the code, and we'll under MoveIt config, under config folder in MoveIt config, there is this gp7 robot srdf file, and if you're using any other robot with any other MoveIt config, so it will name some other, like the file name will be different, but it's always the .srdf file, which is semantic robot description. And here robot move group basically, move group launch file basically loads this into the parameter server, so move like so it can use it. And what it does, this file is basically tells 2-3 different things. One is in a group, what are the links and joints and how they are connected, and what's the chain of it, like, and it all like move group all MoveIt just works with serial chains, I think, right now. Then we have this certain group states. If you see here, these group state is basically the poses that we have defined. So there is this one which connects these joint, which are the, in this group state there is the name is called home. It's the group from ARM, which is basically this group, and these are the joint values. So if I want to add another one, what I can do is I can just simply copy it, or because I'm lazy, so you can write it, paste it, and let's say name it anything, but it should be different, like it makes sense to name different poses differently, so I'll just name it pig. It's from the group ARM, and I can put random values here. It should be within the joint limits which were defined in the URDF, but let's say 0.1, 0.25. I have no idea what it will look like, but yeah. So we have another pose, and there is also, it's easier to see this is a tag called disable collision, which is disabling collision between base link 1 and link 1 because they are physically connected. So when the collision detection is working, so it should not it should disable the collision check for these two because they are adjacent, and similarly like this. So now I save this file and I start GCP launch again. Have this ROS here, and if we go into the goal state and see, there is this pick pose, and if I click on it, oh, it looks exactly like, so this is pick pose and this is the stand up pose. They are different, right? Because I changed the joint values for pick pose. I copied the stand up pose, but I changed the joint values again. So if I execute it, it's like this. Seems to be working, right? Okay, so that's all for today. Probably in the next video we'll see how we can add gripper and simulate gripper, and how we can add a camera and simulate camera, probably kinetic camera from OpenNI, and the plugin will use this OpenNI. Okay, so subscribe to my channel for more tutorials, and like this video, share it if possible. Bye bye.